Last week, we discussed the 4 subway lines passing around the site, the resulting vibration and noise issues, and the construction problems arising from these conditions. To address these issues, we cover the implementation of underground anti-vibration walls for top-down construction. To this end, the existing basement walls of the old government building was utilized on the west side. New concrete walls were constructed on the south and north sides, and earth anchors were installed on the east side. Additionally, we discussed the diaphragm wall, soil and cement slurry missing wall, the expansion joint and vibration isolating pad. Today, our team will go into detail for the placement of vibration isolating pads and the construction wall, which were not covered in depth last week. We will also discuss the overall process of underground construction and our second major focus point, earthquake, particularly how the PC bridge plays a vital role in preventing earth pressure. This is Team 1. Now, let's begin our discussion on vibration isolating pads and expansion joints. The underground structure of the Tokyo International Forum is designed to cover the entire site, consisting of 3-story reinforced concrete structure integrating the glass tower and the hall tower. Surrounded by rail structures on all sides, there is a risk of vibrations propagating to the hall. To counteract this, a design incorporating continuous underground walls to support the external earth pressure and separate the underground structures were implemented. First, let's delve into more details about the vibration isolation structure walls. You can see that the vibration isolating pads are perfectly positioned between the diaphragm wall and the construction wall. These pads are aligned horizontally with a spacing of 600 mm, and arrays of these pads are present at levels B1, B2, and B3, effectively reducing the noise and vibrations transmitted from the subway line through the underground by about 5 to 6 decibels. A model cement board that acts as an external formwork is installed to interface with the vibration isolating pads from the continuous concrete wall. Between this model cement board and the internal formwork, separators and pipes are assembled. The use of model cement boards is strategic as, unlike typical walls, they allow for increased margin space, minimizing the overall space within the margin, while making it easier to integrate separators that connect to the internal structure. Similarly, the internal formwork and separators are installed within the extensions of pipes, and aggregate is poured into the erected structure. The pour structure utilizes molded concrete and an internal formwork composite bound together with separators. These components are not removed later but continue to serve as part of the structural support. So far, we have mentioned that the construction focused on 3 keywords: an earthquake, wind force, and vibration. The vibration issue was resolved through the diaphragm wall and vibration isolating pad. The second key focus is earthquake. Let's explore how this issue was addressed during the top-down phase. First, the ground was partially excavated and underground columns was piled. The spacing was determined by a 9-meter grid designed for the theater hall module. Second, after further excavation, subbase concrete was partially poured. This subbase concrete is not a structural element of the building but serves during construction to secure working space and define partitions. Thanks to this, scaffolding was not necessary during the top-down process. At the Tokyo International Forum, a 50mm thickness of subbase concrete was used. Actual slabs of the building were then constructed directly on top of this subbase concrete, with formwork and rubber placed, eliminating the need for additional shoring. In the third step, V-shaped columns were created for the conference hall, Hall E, B1, B2 level. And additional earth anchors were installed on the east side towards the glass hall. These earth anchors were installed to support the earth pressure that the yet-to-be-constructed underground level 1 slab would need to bear. The fourth step involved the creation of the PC bridge, which is crucial for supporting earth pressure. This PC bridge plays a vital role in ensuring stability against seismic forces by acting as a key structural component, thus mitigating the risk during an earthquake. Do you remember the 3 key points of the construction process we mentioned before? Earthquake, wind force, and vibration. The Tokyo International Forum is designed with underground continuous walls surrounding it, progressively reinforcing the structure to handle increasing earth pressures as excavation deepens. Additionally, surrounding columns and beams are used to resist the pressure from the surrounding soil. However, these measures alone were not sufficient to overcome the earth pressure. This insufficiency arises because the central part of the Tokyo International Forum needed to accommodate an integrated exhibition space across underground levels 1 and 2, known as Hall E. This exhibition hall, which spans a considerable 7,500 square meters, has a structural disadvantage in overcoming earth pressures from all sides. Particularly, the lateral earth pressure acting in the longer direction posed a significant challenge during the construction of Hall E. To address this issue, an aerial PC bridge connecting the glass hall and the concert hall was proposed. This PC bridge, designed as a cantilever beam, is capable of supporting an axial load of approximately 1,000 tons and can withstand 1,007,000 tons of pre-stress, serving as a crucial structural component. The PC bridge was constructed during the fourth step of the underground construction process previously mentioned. The bridge modules have a cross-section of 2.25 meters and a longitudinal dimension of 2.5 meters, comprising a total of 24 PC modules. These modules are combined to create a bridge that spans 60 meters, linking the glass hall and the concert hall. Let's look at the cross-section of the modules. It is designed to accommodate a total of 14 cables and 2 steel bars. The construction process of this PC bridge was carried out in 5 stages. First stage. The PC bridge modules were initially lowered through a temporary opening on the first floor to the underground levels, down to a space set up for sliding on temporary supports. Second stage. The PC bridge modules were horizontally slid towards the outer frame along a slide rail. The sliding surface details of the PC bridge modules show that a 4.5mm steel plate for sliding was attached on the platform side rail, and a dry lubricant film of molybdenum disulfide was created, with a 30mm thick hard polyethylene plate attached on the PC side to reduce friction as much as possible during sliding. The modules were connected by applying epoxy resin on the adhesive surfaces and crimping with PC steel rods. Third stage. Primary tensioning was applied from both sides after inserting 14 PC cables, which helps the bridge gain additional strength and stability before the concrete cures. Subsequently, concrete was poured, integrating the PC modules. Fourth stage. After the removal of rails on the supports, hydraulic jacks were used to handle the axial load of the PC modules. The load was transferred from the first floor slab to the PC bridge using coupler joints, and expansion concrete was poured on the both sides of the PC bridge. Fifth stage. Secondary tensioning was performed due to the loosening of cables under load. The cables on the side towards the glass hall were tightened for additional tension. The concrete work was completed, and the support was dismantled from the center, ensuring that the jacks at the 2 central points could fully withstand the self-weight of the PC bridge. With the completion of the PC bridge, Hull E was successfully able to withstand the earth pressure. In the final stage of the top-down method, the ground was excavated up to 21 meters, fully supporting the earth pressure with the underground structure. The construction then moved to creating the steel skeleton for the theater hall module, the truss structure of the glass hull, and the main columns. This construction addressed the last of the 3 key points, wind force, which we'll cover next week. Next week, we'll discuss the general construction process of the top part and the top-down method, how the main columns that supported the exile load of the glass hull were constructed, and why the stiffness of the main columns had to vary from top to bottom. This was Team 1. Thank you for listening.